Hello everybody and welcome to today's video. Now listen before you say anything. Yep, I know it has been quite a while. I have not posted a bit, but it's only been like say it's been nearly a month or so since my last calculus video on the channel. But today we're gonna be talking about something really special. Gonna be talking about Newton, our big man Newton. Gonna be talking about all of his laws of motion. Yep, you heard that right. All of Newton's laws of motion today in one video. Get prepared. Alright, so first law we're going to talk about is Newton's first laws of motion, which is basically inertia. So Newton said that if I have an object, let's say a ball, and this ball is moving with some acceleration, here is its acceleration vector pointing in this direction, and over time it will keep moving. It will stay in motion. And why is because it has kinetic energy, or in other words, it has inertia. It has momentum. And inertia is a property of matter. Inertia is a really important thing, and there are really a lot of applications of it in real life, in engineering, and what other stuff. For example, if if you're in a bus, right? Say you're in a bus. Let's make a small seat over here. Let's say that this is you. Don't ask me how. Let's say that you're sitting on the seat, and here's the driver with the wheel, casually just driving, and he sees a stoplight, and it's going red. And he was already going before that with some acceleration, with some velocity. He was accelerating. He didn't have a constant velocity, so there was a force acting on it. And that force, we'll talk about it later on. And he was going with some speed, some velocity. And all of a sudden he had to stop. What do you think is going to happen if you weren't seat buckled to your seat, to your chair? You were going to fly out of the bus straight into the street or to whatever with that same acceleration. Hold on, because vectors do matter. You are going to fly out with the same acceleration of it. Why? Because you have inertia. You were at motion, and your inertia was that was your state of inertia, because in order to have inertia, an object can be at motion or it can be at rest. If an object is at rest, it will remain at rest unless it is acted on by an external force. That's what Newton said over here. And I kind of went a bit long to get to the point where Newton talks about external forces, because inertia is a really important thing, and not many people actually think that you understand it. So I had to, take a while to get to the external force part. So just so you know, you're in a bus, get seat buckled. Why? Because you have movement inertia. We have two types of inertia. Just between us. We have movement inertia, where you're at motion, all right? Just like the bus over there. And you have inertia, so you have some kinetic energy that you still want to spend. So you're gonna have to keep going with that kinetic energy or that acceleration, with that velocity. What type of thing that was going, with you? Kinetic energy, whatever the way you want to describe it, because inertia. Or you can have rest inertia, just like this ball over here, unless it is acted by an external force. And in this case, I'm guessing the external force here is going to be the brakes. The brakes which the driver um, hit on, because he also is going to get affected, you know. But drivers may have some more experience than you, even though he's not seat buckled. But obviously, that doesn't mean that he doesn't have inertia. Anything in this bus is going with the same exact speed, velocity, acceleration that the bus is going, unless it is acted upon by an external force. Alright, now you've heard me say the word force a lot in Newton's first law of motion, inertia. Why? Because it is the main idea of Newton's whole work. Newton was describing mechanics. What is mechanics? It has to do with you breaking down the forces that are acting upon an object and understanding why it moves, its momentum. That's a whole package in physics called mechanics. Anyways, so in this video, I'm going to show you how Newton actually himself derived the formula for force. Now, if anybody has any questions about it, you can tell me. It's completely fine. Newton said that force is nothing but the change of momentum over time. And I'm just going to show you, I'll show maybe perhaps the derivation just right after explaining it because it needs calculus and some integration, all of that. But anyways, so he said that it is the change of momentum over time. Well, what is momentum, guys? That's mv, right? But hold on. Change in momentum. Oh, we gotta go back. That means that, hold on, am I gonna have a change in mass or a change in velocity? Obviously, no, you're gonna have a change in velocity, not a change in mass. So that's m delta v over delta t. Hang on a minute. Can I not just rewrite this as m multiplied by delta v over delta t? Of course you can. It's mathematics. Don't learn physics, you don't know what 1 plus 1 is. Now, delta v over delta t, does that not remind you of something? Of course it does. Change in velocity with respect to time. That's what we know. It's acceleration. So yes, force does equal mass multiplied by acceleration. Now I know people are gonna ask, but why isn't it changing momentum? Because that's how nature works, number one. And number two, because that's what mathematics got him to. So I'll say the derivation at the end, but let's take some examples. First, we're going to have to go back to a bit of analytic geometry. Vectors. What is a vector, guys? A vector, it's a physical quantity that has a direction. Forget that. We're going to need to go into the mathematical detail. If I have an object here, say this ball, and I am going to kick this ball in this direction with a force of, say, 10 newtons. Newton is the unit of force, just in case you forgot. Here's the thing, my other friend is also going to kick the ball, but with half what I'm kicking, or with any number. Let's say 5 newtons. What is the sum of the force? And that is what we are learning in this second law of motion. Net force. What does net mean? No, not the net when you play football. No. Net force refers to the sigma. You heard that before? Sigma F, the sum of the force, and sigma here means sum. Sorry about that. So, yeah, Newton here wanted to use mathematics because I have two vectors. See, let's say I have F1 and I've got F2. I want to find the sum of the forces. And you have gravity pointing downwards, so we don't forget. So let's call that weight. And you also have the normal force, which is opposite of gravity. But forget those for now. Don't focus too much on them. I'm going to want to focus on F1, ready? And on F2. How can I find the sum of the forces here? That's simple. Two vectors in opposite direction, or two vectors that have a 180-degree angle between them, half a circle. Then the sigma F here is equal to F1 minus F2. Yes, if two vectors opposite directions, you subtract. If two vectors same direction, So yeah, as I was saying, guys, the video cut out. So if two vectors opposite direction, you subtract. Two vectors same direction, you come on. You should figure this out. I'm not gonna say it. Come on, come on. You add them up, right? Proud of you. Anyway, so now let's subtract them. 10 newtons minus 5. Oh, that's eating up. Somebody ate the 5. Give it back. 10 minus 5, well, that's nothing but 5 newtons. Now, I'm going to give you a second. Can you tell me what is going to be the direction of the net force? Take a second. All right, let's see if you're correct. So again, the ball is from the ball again. We have 10 newtons here, 5 newtons. What are you doing? Direction of the net force on this object will be in 5 newtons to the east. Why, Mr. Zeekop? Because the bigger force had the larger direction. Remember, a vector, it has a larger magnitude and a direction. So 10 minus 5, 5 newtons, but in which direction on the x-axis? On the positive or on the negative? Positive. Why? Because that is where the larger force was. Right now, on to a very, very important one here. And this one requires a bit of analytic geometry knowledge. You took in vectors that if you have two vectors that have the same beginning, alright, their sum will be a direction in the middle, just like this. Regardless of, what the angle is. And that is what happens here. They both have the same point of origin. This is a new color. Gosh, I'm really old. They both have the same point of origin. See? Plus, they have a 90-degree angle between them, so we can apply Pythagoras here. So now, using this knowledge, we can say that the sum of these two forces on this mass M be a direction in the middle like this. That's kind of terrible. I have an idea. Let's be a bit smart. Gosh, what the? Right, guys, I've come to the conclusion that I'm a terrible painter, okay? But I can draw a free body diagram, so don't bully me, okay? So here's the sum of these two forces, just like I said. And remember, you have a 90-degree angle. Hang on, this looks like a rectangle, right? Can I close this and call this 4? Can I close this and call this 3? Yes, you can. Mathematics. Now, saying this, I have a right side angle triangle with a 90-degree angle with lengths. Here is 3 newtons. Here is 4. And I want to find this, because this is the sum. So let's use Pythagoras. Let's call this A, maybe B, and C. AC, that's gonna be AC equals square root the sum of each one squared. So 4 squared, that's 16. 3 squared, that's 9. That's eaten up squared. Put them under the root, that will give you 5 newtons. Alright, so I'm gonna close off Newton's second law of motion with this example because I really like this. So pause the video and see if you can solve for acceleration. Alright? That looks like alpha, but whatever. See if you can solve for acceleration. Pause the video and see what you can do. Give it a shot. Alright, I'm assuming you give it a shot. So let's see. I have here two forces and I have mass. But let's focus carefully. I know that from Newton's second law of motion that F equals ma. So if I want to solve for acceleration, thus, therefore, acceleration A equals, take this on your side, reciprocal, A equals F over m. And remember, this is not just any F, no, this is the net force. So in this case, I have mass. I need to get the net force. Ooh, net force. So the sum of the forces. So I have two forces opposite direction. Yes, Seacop told me if they are opposite direction, I subtract. Ooh, what's this? 10 to the third? That's 1,000. Don't worry, I wrote it in different notation so you get used to it. So let's solve for the net force. That's going to be equal to 1. Hold on, sorry about that. 10 to the third newtons minus 500 newtons, all of that, divided by 20 kilograms. You can solve it real quick, then you'll get an acceleration. Oh, and I want you to find me the direction of it also. So solve it and see if you can figure out the direction. Alright, so you should get a magnitude of acceleration worth of 25 meters per second squared. That's a lot, right? So, okay, take a second, see if you can find the direction of the acceleration. Yep, you were correct. It was this direction. Just kidding. False. Nope. Acceleration was this direction. Why, Seacop? Because acceleration has to do with the direction of the net force, not the direction of the opposite force of motion, not for whatever. The net force, in this case, was equal to 500 newtons due east, due the direction of the larger force, magnitude, and direction. So acceleration, because it is also a vector, it is multiplied by a scalar, so it takes the direction of the vector, which is the force.